Watch an object travel a perfect circle. Its position vector never changes length. It only swings around, always pointing from the center out to the object. So where does the motion actually live? Here is the key idea of circular motion in polar coordinates. The speed isn't hiding in a stretching vector, it's hiding in a spinning one. To find the velocity, we won't differentiate coordinates, we'll differentiate the direction itself. Start with the picture. An object moves on a circular orbit of radius r drawn in the xy plane. The position vector r of t reaches from the center out to the object at a point P on the circle. The polar angle theta of t measures that direction, the angle from the x-axis. Now at the point P, we attach two pairs of unit vectors. First, the fixed Cartesian unit vectors, I hat pointing along x and j hat pointing along y. These never move. Second, the polar unit vectors. R hat points radially outward, straight along the position vector. Theta hat points perpendicular to it in the direction of increasing angle. These two rotate as the object goes around. The position vector is simply r times r hat. To do calculus, we need the polar unit vectors written in the fixed Cartesian basis. Look at r hat. It points at angle theta from the x-axis, so its x component is cosine theta, and its y component is sine theta. That gives r hat equals cosine theta I hat plus sin theta j hat. Theta hat is perpendicular to r hat, rotated 90 degrees counterclockwise. Rotating by 90 degrees sends cosine theta to minus sin theta and sin theta to cosine theta. So theta hat equals minus sin theta I hat plus cosine theta j hat. These two expressions are the whole game. The Cartesian unit vectors I hat and j hat are constant in time. All of the time dependence now sits inside cosine theta of t and sin theta of t. Differentiating becomes pure chain rule. Now differentiate r hat with respect to time. R hat equals cosine theta I hat plus sin theta j hat. Since I hat and j hat are constants, we only differentiate the coefficients. By the chain rule, the time derivative of cosine theta of t is minus sin theta times d theta dt. And the time derivative of sin theta of t is cosine theta times d theta dt. Substitute this in. The derivative of r hat is minus sin theta d theta dt I hat plus cosine theta d theta dt j hat. Every term carries a factor of d theta dt, so factor it out in front. What's left inside the parentheses is minus sin theta I hat plus cosine theta j hat. But we recognize that vector, it is exactly theta hat. So the time derivative of r hat equals d theta dt times theta hat. Differentiating the radial direction gives you the tangential direction, scaled by how fast the angle is changing. That single fact is the engine of everything that follows. The calculation for theta hat works the same way. Theta hat equals minus sin theta I hat plus cosine theta j hat. Differentiate term by term. The derivative of minus sin theta is minus cosine theta times d theta dt. The derivative of cosine theta is minus sin theta times d theta dt. So the derivative of theta hat is minus cosine theta d theta dt I hat minus sin theta d theta dt j hat. Factor out d theta dt again. Inside the parentheses, we have minus cosine theta I hat minus sin theta j hat. That is the negative of cosine theta I hat plus sin theta j hat, which is the negative of r hat. So the time derivative of theta hat equals minus d theta dt times r hat. Differentiating the tangential direction points you back inward along the negative radial direction. The two unit vectors feed into each other as the object turns. Now we can find the velocity. Velocity is the time derivative of the position vector. The position is r times r hat. The radius r is a constant since the object stays on a fixed circle. So velocity equals r times the time derivative of r hat. We just computed that derivative. it is d theta dt times theta hat. Therefore, velocity equals r times d theta dt times theta hat. Look at what this says. The velocity has no r hat component at all. There is no radial velocity. The motion is purely tangential, pointing along theta hat tangent to the circle. That matches our intuition. An object on a circle moves along the circle, never toward or away from the center. We name the tangential component v sub theta. So v sub theta equals r times d theta dt. The velocity vector is v sub theta times theta hat. The radius sets the scale, and the d theta dt, the rate the angle sweeps, sets how fast the object moves along the curve. Two final definitions tie it together. We write the magnitude of the velocity as v, the speed, and we give a name to the rate the angle changes. The angular speed is the magnitude of d theta dt. We denote it by the Greek letter omega. So omega equals the absolute value of d theta dt. The absolute value matters. The object can sweep counterclockwise with d theta dt positive or clockwise with d theta dt negative, but its angular speed omega is always positive. With this, the speed has a clean form. Since the tangential component is r times d theta dt, the speed v equals r times omega, radius times angular speed. So the whole story of velocity in circular motion comes down to one move. Differentiating the rotating radial direction, r hat turns it into the tangential direction, theta hat. The motion was never in a stretching vector. It lived entirely in a spinning one. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.